Hey guys, this is Mr. Mitchell. Today we're going to be talking about kinetic energy. So first of all, what is kinetic energy? We've talked about this in the past. We want to just recall that kinetic energy is the type of energy that an object has because it's in motion. So we have an example down here, right? A dude is pushing a ball down a hill, and so when the ball is at the top of the hill like this, it has a lot of GPE, and then as he rolls it, it starts moving and picks up more kinetic energy as it rolls down the hill. So kinetic energy is the energy of motion. Some qualitative properties about kinetic energy. Remember, qualitative is just kind of like a verbal explanation. The amount of kinetic energy that an object has depends upon two things: the mass and the velocity. So as an example of the mass, right? If I were to have a huge tractor trailer truck and it's going 60 miles an hour, and I have a baseball, and the baseball is also going 60 miles per hour, right? Which one do you imagine has more energy? Obviously, we're going to go with the truck, right? I'd rather get hit by a baseball going 60 miles an hour than a truck going 60 miles an hour. And that's because the truck is carrying more energy, and that's because the truck has more mass. So the kinetic energy of that object depends upon its mass significantly. The other thing that Ke depends upon is the velocity of the object. So I have two baseballs, they have the exact same mass, but let's say I throw this baseball with the speed of, 50 miles per hour, and I have an MLB pitcher who throws one that's 102 miles per hour. Again, if I have to pick between these two to get hit by, I'm going to go with the 50 mile per hour ball because it's carrying a lot less energy. It's going to hurt me quite a bit less. So we see that the kinetic energy of the ball depends also on how fast it's going, or depends on how fast the object is going in general. So let's take these together, right, the mass and the velocity, and then let's make a quantitative property. How can I calculate exactly how much Ke an object has? So since it depends on mass and it depends on velocity, we know that they're going to be included in the equation. And so the actual equation comes from Ke equals 1/2 times the mass of the object times the velocity of the object squared. All right, so when we do these, we want to know that the velocity is the item or the term that gets that squared function. So let's just do a practice problem. We've been doing this pretty consistently so far, and so we're going to use the same system. So it says, while running the 100-meter dash, Usain Bolt has reached a top speed of 12.27 meters per second. If he has a mass of 94 kilograms, how much Ke did he have when he reached his top speed? So we always want to identify the question first, right? And so that is saying, how much kinetic energy did he have when he reached his top speed? So that's the question we're looking for. We want to write down our givens here, okay? So in terms of the givens, we can read again. While running the 100-meter dash, Usain Bolt has reached the top speed of 12.27 meters per second. So we know his velocity is going to be 12.27 meters per second. If he has a mass of 94 kilograms, all right, so we now know his mass is 94 kgs. How much Ke did he have when he reached his top speed? So we have our two givens here. Notice that it says the 100-meter dash. Just because it's a number doesn't mean that I'm going to include it, right? That's just telling me the race. That has nothing to do with calculating the kinetic energy. So we go over here, we're going to write our equation down. All right, so Ke, if you remember, is 1/2 the mass times the velocity squared. So now we're going to go down and write in our work and solution. Okay, so what we'll do here is we'll rewrite the equation first. Ke is 1/2 mass times velocity squared. And now we're going to just substitute in the items here. So 1/2, I'm just going to rewrite that as 0.5 because it's going to be easier later when we go to multiply. So 0.5 and 1/2 are the same. Now I'm going to replace the mass. Well, the mass was 94 kilograms. So I'm going to put 94 kilograms. And then I have the velocity, which is 12.27 meters per second. and I know that the velocity term has to get squared, so I'm going to square that guy. So if we think about the order of operations, remember, please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, and then subtraction. That's the order that we have to do our math. So if we're looking at this problem, now we have this kind of interesting squared term. Well, that's going to be the first thing I have to deal with because the parentheses are just holding one number. Then I have to deal with my exponents. So before I go anywhere, I'm just going to copy the first part down exactly the same, and we're going to square that 12.27 and write down what that is. So 12.27 squared is 150.6 roughly, and since it's meters squared per second squared because of the squared term. So then the last step is going to be now to multiply all three of these numbers together. So when I multiply 0.5 times 94 times 150.6, I get 7,078.2. And remember, we're measuring energy, so we're just going to forget all these other units. We're just going to call them joules because that's what energy is measured in. So that is my work and solution. My last step is going to be to communicate that in a complete sentence down here. So how much KE did he have? Usain had 7,078.2 joules of KE at his top speed. And that's it. Very straightforward. Same way to organize the problems. We just have kind of a unique situation now with our new equation, and we have to remember to square that one term. So we know that KE depends on mass and it depends on velocity. But as a quick question, what do you think the amount of KE depends on more? Does it depend on the mass more, or does it depend on the velocity more? Meaning, if I were to change one of those two numbers, what would create the largest change in the kinetic energy? So let's go through an example here, just a real simple one, to see if I change something up, what effect it has on the kinetic energy. So let's say you have a pitcher, he's going to throw a baseball, right? A baseball has a mass of about 0.5 kilograms, and he's going to throw it 25 meters per second. So if I go through all the math for this, right, I know that the mass for this is going to be 0.5 kilograms. And then the velocity is going to be 25 meters per second. Let's say I go through and calculate how much KE that has. I did that earlier, and I found that it has KE equals 156.25 joules. All right, 156.25 joules. You can check them out later if you want to. Let's say I take the mass and I cut it in half. All right, so instead of 0.5 kilograms, I'm actually going to have a mass that's going to be 0.25 kilograms. And I'll keep the velocity the same. We'll say it's 25 meters per second. When I calculate that, I get a kinetic energy of 78.125 joules. All right, so my KE has gone down. Obviously, I cut the mass in half, and so it should go down. But what happens if instead of cutting the mass in half, I cut the velocity in half? The mass is still going to be, going back to the original here, 0.5 kilograms. But now instead of 25 meters per second, I'm going to cut it in half, and that's 12.5 meters per second. When I calculate the KE there, I don't get the same number as this. All right, what I get is 39.06 joules. So in the first example, all I did was change the mass. And in the second example, all I did was change the velocity. So what caused a bigger change in my KE? Well, if I look, right, I started out with 156.25. When I cut the mass in half, I went down to 78.125. It's about half of that, okay? But when I go over to cutting the velocity in half, I've made a much bigger change, right? I've gone from 156 all the way down to 39.06. So what is going to influence our kinetic energy more? The velocity is influencing it quite a bit. So what's the reason behind that? Why does the change in velocity change it more than the change in mass does? Well, the kinetic energy is 1/2 mv squared, right? The squared goes with the velocity term. So when I had no change, right, we had 156, I should have just left that in there, 156.25 joules. When I halved the mass, I had 78.125 joules. And when I halved the velocity, I get 39.06 joules. So we see that the largest change happens because I have a term that gets squared, right? When I cut that velocity in half and now I square it, it's going to be way more significant. So since the velocity term is the one that is squared in our equation, that is going to be the one that has the greatest influence on kinetic energy. So since velocity term is squared, it has a much bigger influence on kinetic energy than the mass does, because the mass I'm just multiplying, whereas the velocity I'm multiplying and squaring. Okay? So hopefully that helps you out a little bit. You have a better idea how to calculate kinetic energy. We obviously knew what it was before, but we also can apply the formula to recognize that the squared term is going to have a much bigger influence on the kinetic energy as a whole than the term that is not squared. All right?